Hello, my name is Heaven, and I'm a student taking ideas in math, and I would like to give a simple explanation of the Frobenius problem. My introduction to and understanding of the Frobenius theorem, which is also commonly referred to as the Frobenius corn problem, came first from an example based in everyday life, a simplified version known as the Chicken McNugget theorem. So, to first relay this theorem to you, I will describe this intriguing issue posed by ordering takeout. In the simplified version, we are told that chicken McNuggets are sold only in boxes of 6, 9, or 20 nuggets. To Henry Picciotto, this poses the question: what is the largest number of McNuggets that you cannot buy exactly, given that we can only purchase in values of the provided increments? So our goal with this problem is to first find non-McNugget numbers. Those are numbers. Those are any numbers that cannot be generated from just 6, 9, and 20. So like first 1 through 5 is not possible because 6 is the smallest box that we can use. 6 of course works because that's just like one of our units that we already have. 7 and 8 don't work because they fall between 6 and 9, and we don't have like small enough units to fill the gap. 9 works because it's one of our existing units again. 10 and 11 don't work because 6 is too small, 9 is too small, but if you combine them, or any combination of those two units, then you get a number that's too large. 12 works because it's just 6 plus 6. Then 13 and 14 are not possible because 9 plus 6 is too large, but 6 plus 6 is too small. And then that continues, but you can see from like the slide that a similar logic is followed like as we continue. But the important thing is that if we keep going, we find more numbers that don't work, such as 22, 23, 25, 28, 31, 34, and 37. So now let's just skip to 43. If we use two of the largest nugget boxes, the 20 ones, for example, we can only get to 40, but then this doesn't leave us with any possible units to use. And you can see, like, as you keep trying with any other integer combinations of 6, 9, and 20, however, like, these numbers don't allow you to get to 43. So for now, let's just, like, mark this as another non-McNugget number, but we need to know if there will be more after that. So just like as a bit of a quick check, let's look at the numbers that come after 43. First, we can see that 44 works because you can start with 20 and then add 4 6s after that. As a side note, there's actually like another way of doing this, of course, by adding 20 plus 9 plus 9 plus 6. But that will be the case for many larger numbers, and it doesn't really matter as long as there's one possible combination at least. Next, 45 works because we can just add 5 9s. And then next, 46 works because we can just do 20 plus 20 plus 6. We can see from this like integer partition in this picture that the breakdown of numbers after 43, like we can see like a pattern of combinations of 6, 9, and 20 that works for all the subsequent numbers after 43. And this pattern works even for numbers that are not on the chart. So what's happening is that after you reach a certain point in which consecutive numbers work, and in this case those numbers are 44, 45, 46, 47, 48, and 49. So after those consecutive numbers, then every number afterwards can be formed because you can just keep adding 6 to the previous working numbers. So a Frobenius number is a special number that specifically defines the largest number that cannot be made from a set of numbers. And since 43 is the largest non-McNugget number out of all 22 non-McNugget numbers, that makes 43 the actual Frobenius number in this case. So I would just briefly discuss like the general form for now because I want to return to it with a little bit of like a more simplified version that only has two numbers. But here are some things to know about the mathematical representation of this problem. So for the McNugget problem, n equals 6x plus ny plus 20z, and here x is how many how many 6 boxes that we would use, y is how many 9 boxes we could use, and z is how many 20 boxes that we could use. And of course, we can only have positive numbers of each box, or 0 of each box assigned for each. Um, so, like as a brief a short brief history of the Frobenius problem. First, the mathematician Ferdinand Frobenius studied the problem in the late 1800s, but he only presented it in lectures, and he never actually published a formal paper on it. And in 1882, Sylvester worked on the version that only has two numbers, and he found a formula where g of a and a1 and a2 equals a1 times a2 minus a1 minus a2. And then the McNugget version actually came much later. It became popular through a magazine and a textbook in the 1980s by Henry Picciotto. And that was our earlier example in which the McNuggets were being sold in boxes of 6, 9, or 20. So for our next problem, we're going to generate values using combinations of 3 and 7 only. So you can see that we can get numbers like 6, 7, 9, and 10 using this combination, but we miss out on numbers like 1, 2, 4, 5, and 8. So let's jump to the value 11. If we use three threes, then we can get 9, and we still need 2. If we use 1, 7, we get 7, obviously, and we still need 4. And if we use 3, if we use 1, 3, and 1, 7, then we can get 10, but we still are left with like 1 that we still need. And so with this like simple inventory with only the numbers like 3 and 7 available to us, it's much more obvious that there's no combination of these numbers that works for 11. So clearly 11 cannot be written in this form. Also, we can check like a few numbers after 11. Like, for example, we can make 12 with 3 times 4, and then 13 with 7 plus 3 times 3, and then so on. And actually, all numbers after 11 work with some combination of 3 and 7. So that tells us that 11 is the largest of the failing numbers. And so now let's just like generalize what we just did. Instead of 3 and 7, we can use like any two numbers, a and b, or a1 and a2, depending on how you write it. But we can use the formula of n equals a times x plus b times y, where x and y are whole numbers greater than or equal to 0. And that's a representation called a Diophantine equation, which just means we're solving for integer values, like positive numbers. So it's a very useful formula to find n, or like the largest number that cannot be written using the two numbers a and b, rather than using the brute force method. So anyway, so the general form is GAB equals AB minus A minus B. We can go back and like apply this to our second example, our most recent example, again, where A is equal to 3 and B is equal to 7. If we plug in our values for A and B into the GAB, into the G of A, B equation, then we would get 3 times 7 equals 21, and then 21 minus 3 equals 18, and then 18 minus 7 equals 11. And that's like the exact number that we found through this brute force method earlier, like here. So for an even more expanded value set where you have like more than 2 possible values that you're allowed to use, we can expand it even more to write n equals a1 times x1 plus a2 times x2 plus a3 times x3, continued up to ak times xk. And the largest number that cannot be written with numbers a1, a2, a3 through to ak is then the Frobenius number. And thanks to this formula, we don't have to test each subsequent number one by one with the brute force method. And it tells us that there will always be a largest number in terms of like what number we cannot write with ax plus by. But then every number after the Frobenius number is possible to represent with a given set of numbers. And the Frobenius theorem is like very widely applicable, of course, and thanks to the University of Waterloo for this. But so, for example, when making change, you can combine coins only of certain values, and that theorem tells us that there's like an actually more optimal method to the U.S. coin system. And then there are like also theoretical examples of math and computer science, like the shell sorting algorithm, which is a method for sorting numbers, and also the deterministic finite automation, which lets you repeat loops of certain lengths to find which steps are not possible. So this is a very useful tool. Thank you.